Today, we're going to continue the study of kinetics. And, I want to make a point again on why do we study kinetics. And we do this because we want to know what's causing motion, right? So in chapter 2 and 3, we look at motion, kinematics. Excuse me, can you please wear your mask properly? Yeah, you need to cover your nose. Thanks. So we were looking at what causes motion. What was motion, how to describe it. And now we need to know what is causing motion, which is forces, right? But I really want to make a big point about the fact that the kinematics that we studied in chapter 1 are particularly useful for this chapter, for chapter 4, because we're looking at particles, right? Chapter 1 was about particles. And then we went through these, but I think it's important to, make a point about it, is that essentially what we're doing in chapter 4 is finding forces, right? And then we need to remember chapter 1 to get our accelerations, right? So if we don't have enough equations from kinetics, we need to apply kinematics. And those are going to be to get some equations that allows us to solve this problem. And then most problems that we have solved so far have been using Cartesian, or maybe they have used a path to solve it. But, also there is a possibility that polar may be useful. And then I'm going to make a point of this, that path, when we describe an acceleration vector in path description, it only has 2 components. So how am I going to do that? Well, let's do this problem first. Let's do this conceptual problem. It's on page 270. So we have a particle, and we are given the velocity of the particle. And that particle is subjected to some external force, right? The particle has a mass as well. And then we are asked to determine the rate of change of speed of this particle. So it sounds a lot like, and then how is it changing? Is it increasing, decreasing, or constant? So it is really, if you read these and you didn't have the vector for the force there, you would try to approach this from chapter 1 type of perspective. It's classical problem from chapter 1. But we don't have enough information because we don't, for instance, we don't have a path, we don't have anything. We just have the velocity and the force. So the fact that we have a force then implies that we will use kinetics. And when we use kinetics, we first start with the free body diagram always. So which forces are acting on this particle? Which force? It's just the external force that is applied, right? We just have this one force. And we are given that force as it should, as a vector. Forces are vectors. Do I need to write the velocity here in the free body diagram? No, it's only forces. So the free body diagram is connected to the left-hand side of Newton's second law, right? Whatever happens on the right-hand side is not part of the free body diagram. It's part of the kinetics. It's part of the kinetics diagram that sometimes Professor Rhodes uses on his solutions. But I don't like to mix them because sometimes, the concept of free body diagram gets mixed. So I always like just to keep forces. Okay, so we need to write the equations Newton's equations for this mass. And, you know, I have said this, but it's important that we remember it. This is a vector equation. And this is a three-dimensional space. So we have three. We need three of those. So we have the vector equation for forces, the component in the x direction. This is what this means. So we have that the component of this applied force in the x direction is equals to the mass times acceleration, right? This is just Newton's second law. So we know that this is 100. So the acceleration is going to be that component, 100 divided over the mass. What about the summation of forces in the y direction? We take a look at this vector. What can we say about the force component in the y direction? It's 0. So then the acceleration, it's also 0. And then for the z component, then it's the same story as for the x component. Okay, so what's the deal here? Okay, we have two equations that give us some information about accelerations, right? But the question is not directly what acceleration does the particle have, but what is the rate of change of speed? So where do we find the rate of change of speed from? Which kinematical description do we use for that? Yeah. Path, right? So by this time, most of you already know this. So we write the path equation. Okay, that's good. The acceleration equation in path. Now we need only this component. But what we have is we have the acceleration in Cartesian, right? Recalling that this guy is 0. So what do we do? How do we find the rate of change of speed if we actually have the acceleration component in Cartesian? We use projections. So first thing is to remember that this v is the speed, right? So how can we find the speed? Speed is the magnitude of the velocity. Even if it's three-dimensional, you know, it's the same story. Now, let's ask a question here. Let me ask a question here. Where is the tangential component pointing in this particle? In the direction of the velocity, right? We need to know this. And what about do we know in which direction is the acceleration? In which direction is it? It needs to be. I need to hear a chorus of this, otherwise it's going to be tricky. So where is acceleration pointing? In the direction of the force, right? The direction of the force and acceleration is the same because they are equal except for a proportionality constant, which is the mass, right? A constant of proportionality doesn't change the direction of a vector. So then the acceleration is going to be somehow, so the mass is greater than 1, so the acceleration is longer than the force vector. So if we have the acceleration vector and the force vector, do we know or can we approximate more or less where the normal component is for, the normal component that accompanies the tangential component in path is? Yes? Perpendicular to the tangential, right? But in 3 dimensions, we have 2 perpendicular directions. It can't be, and only one is right. So it can't be, for instance, perpendicular here on this plane, or it can be perpendicular here on this plane. Which is the correct? If we know the acceleration, and we know that the acceleration does have a component in the normal direction, which of those perpendiculars do I need to, by force, take to be able to actually have the vector of acceleration that I have? Oh, no. You can only have 2 perpendicular directions on 3 dimensions, right? So whenever you have x and y, you have z fixed. But whenever you have z and y, you have x fixed, and so on, right? You can only have 2 mutually perpendicular directions on 3D. And those directions are the ones that I have shown there. So only one is the right one. And this one is given by the vector of acceleration. The vector of acceleration needs a component in the right normal direction. So which is the right normal direction then? The one that is up, right? Because I need this component to get that vector. Do you guys see that? No? If I don't have that normal direction, but I have this normal direction, how can I build a component that is out of the plane? It's impossible. Do you see that? Yes? Because you also have the tangential component. Yes, you're right. But this plane is like this. Do you see that? No, the acceleration vector lives on this plane. Maybe my drawing is not perfect, but if you make a projection of the acceleration, it's there. And if you make the projection of the acceleration, it's there.
Missing the component of A is out of the plane because the plane is angled and A is the have a component in the X direction and figuring out that one.
Okay, so yeah. Okay, hang on a minute. Let me get this right. So we have. Let me draw this again. This is our tangential component, right? Because the velocity is pointing in that direction. The velocity is pointing in this direction. And then we have an acceleration component that is going somehow up in this direction, right? And then I say, okay, I need to have a perpendicular component such that I can get my normal acceleration. So if I take the projections here and the projection here, okay, maybe it's not, I see what's the point. Your observation is, maybe what I need to do is, this is not aligned with the K direction, okay? It's not aligned with the K direction, but it's kind of up from the plane that I originally draw, right? Because what I know for sure, what I know is that the velocity has only components in y and j and what, x and y, right? So the velocity does live on this plane. Now the force has two components, one in k and one in x, but it doesn't mean that it's pointing just straight up, right? It can have a little bit of an angle. So the normal component is not aligned with k. Sorry, pardon my drawing, but it does comes out of the original plane that I draw. So why do I also do this? Because we can find VP by projections with the vectors, right? Or we could have done it in this way. We could have said, all right, I know that my velocity is pointing in this direction. I know that my acceleration has to be in the direction of the force. And once I draw my E normal and E theta, I can know whether VP is increasing, decreasing, or constant. So is the rate of change of speed, what is it? Is decreasing, increasing, or constant based on the vector? We didn't do the dot product. It's increasing, right? Because the component of the acceleration into the E theta direction is positive. It's in the same direction as E theta, right? So these are the two ways in which you can work out this problem. Now, why did I take so much time to do this? Because first thing, the acceleration, the vector can be expressed in any coordinates that you want, right? And we have taught you three: Cartesian, path, and polar descriptions. And the big thing that I want to make here is that in path description, the acceleration vector, by virtue of path being so powerful, will only have two components, always, right? Even if in Cartesian it has three components, in path will have two components. And this is important for the problems that you are solving, the problem that is needed today, right? And it's kind of tricky because this problem, has to do with this challenge question in page 888. It's this question about what is the centripetal force that we have been maybe spoken in previous courses. Well, the centripetal force is the effect of the acceleration. So it's on the right-hand side of Newton equation, so we don't write it on our free body diagram. But more importantly, what I wanted to make a point here between these two problems is that this problem that we did in class and this problem that you have to do today, in procedure terms, are the same. I mean, okay, there is one difference. You need to find tensions here. So the tension part is new, but the rest is the same. You have to find some kinematic equations. You need to use path. And in the same way that if I draw here, actually in this case, I'm going to try to draw the path that this is following. So it's a circle like this. Maybe I need to make a better attempt. So it's a circle like that. The tangential component, it's on the plane, and the normal component, it's on this plane. So on this view, the tangential component is like this. and the normal component is like this, right? It was the same for the car, but in this case, the tangential component is like this and the normal component. And when I draw this parallelogram is to show that they live on the same plane. And that plane is the plane that coincides with the, in this case, the x direction. And then we use the fact that the velocity, it's in the tangential direction. The speed is the magnitude of the velocity. Path, we have only, in path, we can get the rate of change of speed, and that we have only two components. So for this problem, ET and the normal component, they live on the same plane as the x and z components. And if we have the acceleration in Cartesian, will have ax az, az, and what are we going to have in the y component? 0, right? Because this guy lives on the z, on the zx in plane. And this is a very important concept that you need to grasp. There is no third component in path. It's always two components. All right? Any questions about this? Okay, please take a look at those two problems. Sorry, at that conceptual problem. And go over it because it's really important. It really shows the concepts that we need to know. Okay, let's do now. Okay, I want to again, please encourage you to follow this particle kinetics procedure. Let me do something because I actually want to. Yeah, also for the homework, if you go to this animation, it's called Influence of Speed in Cable Tensions. And it's the same animation that we have. But here we see what the tension is as the velocities change in direction, all right? So this in combination with what I said should help you better visualize this, which is the homework problem, all right? Okay. So in some of the questions I've got on the help room, I still see that many of you are not following this procedure. Please follow it. It helps. It really helps, all right? First free body diagram, then kinetics equations, and then if you need equations, we look for the kinematics, and then we solve. So let's see that applied in problem 4A10. So this problem, we have a particle with some weight that it's moving on a slot. There is something important that I wish you guys to pay attention. The problem says the arm is rotating within a horizontal plane about end O, and we're given some constant rate of motion. And we're also told that the slider is being pulled with a constant rate r dot. So we have the particles, weight, we have the angular rotation of the whole assembly. We have that the particle is being pulled with a certain speed, and we're told that there is a horizontal plane. Everything happens on a horizontal plane. And we need to find the tension, the normal force, and what we discussed in the previous class. In which of the surfaces is that particle leaning on? On which, sorry, of the surfaces? Okay, so I didn't delete the forces. So these are the forces, right? One from the surface in which the particle is leaning on, and one from the cable, right, that it's pulling on it. I assumed that I have a normal force that is pointing, diagonally upwards. What does it mean? Does it mean that I'm assuming that the particle is touching the upper surface or the lower surface? The lower surface. Now, this is only an assumption. And I'm going to let my equations tell me whether my assumption is correct or not. Okay? So, am I missing any forces here? Does anybody see a force that is missing? Yes, Jason? Gravity? What about gravity? It's a horizontal plane. So, guys, please don't lose points on exams and homework because of that. I see gravity drawn in these problems, and then all your efforts, go to waste. So, whenever you guys read horizontal plane on a problem, please underline it, write it, do something, but don't forget about it. It means that everything is happening on a perpendicular plane to where gravity is acting. So gravity is not affecting what's going on in this problem. That's what it means. So there are no missing forces. Okay. So that means that we have, we could use Cartesian to solve this problem. Then those of you who were paying attention know the answer already. But is there a kinematical description that makes our life far easier with this type of problem? Polar, right? There is something happening diagonally, and there is some rotation. So we can use polar and polar is going to make our life far easier because we will see that, the thing we're told when the distance from 0 to the particle is. So what we're going to see is that this tension, is this tension aligned with the ER direction? Do you see why, right? Because in polar, the trick about polar, why is it useful, is because ER, it's always following where my particle is. That is the trick of polar and why it's helpful. So if the tension is in the cable direction, then it has to be in the ER direction. So we have mass, which is weight over G. Now G is not playing a role because it's perpendicular, but still the mass is the weight over G, and we're given the weight because it's in imperial units. So we divide over G equals to the acceleration component in the radial direction. It's equals to tension. So is this tension negative or positive in my polar description? What is it? Negative, right? Because it's pointing inwards. So that's important to get that one right. And now normal. So the normal force, is it aligned to any of these directions, to the radial or theta directions? It's aligned with the theta, right? And I assumed this guy, because I knew I was using polar, to get my normal force positive. Then I have two equations, two unknowns. If you do this in Cartesian, you have to do a lot of projections. You can do it, but you have to do a lot of projections. So we have two equations, and now we have how many unknowns? 1, 2, 3, and 4. We don't know much yet. But we have kinematics. So what kinematics can we use to help us solve this problem? We can find accelerations from the information we have been given, because we can write the acceleration in polar. And this equation is independent from Newton's equations, right? Okay, so we go back a little bit and we check. Maybe I didn't read everything so correctly. So constant rate of R dot. So constant rate R dot means this guy is 0. And, no, actually I did read it properly. I just didn't say it. And omega is constant, so this guy is 0. So we get slightly simplified equation. You know, the ER component, and we have the E theta component. So we have a third equation, but we needed two. What's going on? What am I missing? Exactly. We actually have 4 equations, because we know now that we can do the components. It's a vector equation. So then it's straightforward matter of taking this guy is the ER component, this guy is the E theta component. Then here this guy is positive. And here are our 4 equations. Four equations, 4 unknowns. We can solve it. So this one is fast. I'll solve it till the end. So using equation 1 and equation 3. So here it's equation 1. It's just for the tension. So we need to substitute this guy into this one. That's easy enough, right? Negative R theta dot square, it's equals to minus tension. So then tension, it's equals to everything positive there. And then for the other equation, we use equation 2, and we do the same story. We replace, we substitute for the acceleration, the A theta, which is this guy here, to R dot theta dot. It's equals to the normal force. So the normal force, it's equals to that, right? Okay, so we found tension is that we found normal force is these. So those were 2 parts of the questions. Now we need to check whether I am on which side I'm in contact with. So we need to go and substitute and check. It's my normal, essentially, I said, or I assumed that my particle was touching the bottom surface, and hence the normal force was pointing upwards, which means the normal force is positive. So if the normal force is positive, then my assumption is correct. And I say, okay, it's in contact with the bottom surface, which is a side B. So let's check if that is correct or not. So we go here and we say, all right, the numbers we have is that R dot is negative and this omega is positive. So we have a negative sign here and a positive sign here. So my normal force, in fact, is negative. So which side is it in contact with? Side A. So in fact, it's leaning on side A. Now, you don't have to go and change everything. You already had the answer, right? It's negative, it's pointing in the other direction. You don't need to go and redo everything. The equation has told you whether you were correct or not. Any questions? You guys have doubts? No, you're okay? So, straightforward problem. Now, please, I don't have time to do this one, but try this one, all right? Try it in advance. You're going to be rewarded if you try it. All right, let's try then this one. I will not be able to finish it, but I will be able to set it up. So now, when you see the problems of your homework for Wednesday, it's going to be quite clear that I'm again helping you guys with one problem that is very similar to one of them, and then another that is very similar to the other one, okay? So this one is similar to which problem? The one we just did, right? A little bit more complicated, but you know, use polar, all right? Now, problem 4A8. Okay, we have blocks A and B, which are constrained to move along a smooth vertical and horizontal guides as shown in the figure. A and B are connected by a lightweight rod. This is important. When we have lightweight rod, means the rod has no mass, right? And then there is a force acting on B. There is a force, external force acting on B. And then A is moving downward with some speed. And at the shown position, SA it's equals to 1.5 meters. And then we're asked to find the acceleration of A, B, and the force in the rod, all right? Okay. So remember, we have this whole system connected, but we need to find accelerations. So we need to break up the system, right? Don't try to put your system as a whole. If you put the forces on this guy, you're going to not get the right answer. So which forces are acting on block B? What else? Okay, so this guy is not a cable. It's a bar. But this bar is what you guys called in statics a two-force member, right? The force is transmitted along the direction of the bar. So this is important for your homework, everyone, because in your homework, on this problem, you're told that this bar, even if it's curved, it's a two-force member. So the force is going to be only in one direction, okay? I mean, it doesn't mean one direction, doesn't mean in X or Y. It means it will have, you know, a certain diagonal direction, but it's the same on both masses. That's what it means. Okay, so if that is the case, then the forces on block A are normal force. Maybe I need a name change. In here we have the gravitational force, and then we have the force of the two-force member of that rod. Now, what is different between a rod and a cable in terms of the force? Yes? Exactly. Lightweight rods can have negative or positive forces. They can sustain tension and compression, right? I can compress this pen, but if I take a cable and I compress it, then it just bends. It doesn't carry compression, all right? So this is helping you to solve the problem that is due today, right? Tension can only be positive on cables, essentially. That's a condition that you need. Okay, so now this problem is not difficult in terms of the kinematics or anything, or the procedure. It's a little long, so we need to set it up in an organized way. You know, the kinematics here are actually good in Cartesian because of the way things are moving. So we're going to do Newton's second law in Cartesian. So for block A, we have a negative normal force, a negative member force with an angle. So this is going to be theta. By trigonometry, this is theta. So this is cosine theta. And this equals to the mass times acceleration. And then in the y direction, we have negative FB AB sine theta, negative MAG, it's equals to the acceleration. So this is telling us something about FAB already, but let's just continue. Let the equation speak. And we have the geometry, right? So the angle we can find with SA and SB. We're given the length, so we can find SB. Or we can just write everything in terms of S, you know, yeah, we need to do some trigonometry to get SB, but it's not difficult. All right, so the same for the block B, for block B. So in block B, we have, in the X direction, we have the applied force, we have positive FAB, and here is cosine theta once more. And then this is equals to the mass times acceleration. And then in the y direction for block B, we have a positive normal force, negative weight, and positive FAB sine theta. Then, of course, in here I wrote implicitly FAB by Newton's third law, action, reaction, they need to be of equal magnitude and opposite sign, right? So I wrote them the same, but I changed the signs on my free body diagram. All right, so I have 4 equations, and then I need to count unknowns. I have 1 unknown, 2 unknowns, 3 unknowns, 4, 5, 6, or maybe I didn't count correctly. 1, 2, 3, 4, 5. Up until here, there are 5, 6, 7, and 8. Why did I get 8? Ah, yeah, what I'm up at, sorry. Okay, so 7. Okay, so I counted properly on my cheat sheet, 7. So we need to find 3 kinematic conditions. Now, 2 of them we can find in 30 seconds. What do we know of the kinematics of this problem that is super, straightforward? Exactly. So the acceleration of the blocks, the x acceleration of block A, it's equals to 0, and the y acceleration of block B, it's equals to 0. They are constrained to their axis. Where do we get our 7th equation from? We have this other constraint. The bar imposes a constraint. The length of the bar doesn't change, which means that L square, it's equals to SA square plus SB square. And then we take derivatives. And with the derivative, we found, now this derivative is 2SA times SA dot plus 2SB times SB dot. This is the 7th equation. But we actually need an 8th equation because the 7th equation introduces a new unknown, SB. So we have to, and actually this doesn't help us because we need acceleration relationships. So we need to take a second derivative and find acceleration. So I don't have time to take it. But then you have 8 equations and 8 unknowns, and you can solve the problem, okay? So this is essentially more or less what you need to do for your homework. And you need to be organized. This is why I give you these 4 steps, because you have 8 equations and 8 unknowns. So it's quite a bit of algebra that you need to do.